My name is Daniel Olal, and this is a summary presentation for csci e63 Big Data Analytics course. The goal of my project is to use a big data stack to predict the presence or absence of cardiovascular disease given a set of 11 features. Cardiovascular disease is a leading cause of mortality in the US, with up to 600,000 case fatalities being reported each year. It is estimated that cardiovascular disease costs the US economy upwards of $200 billion every year. The cardiovascular dataset was derived from Kaggle and comprises 70,000 observations and 11 features. The features can be divided broadly into three different categories. Category 1 is the objective features, which are factual, such as age, height, weight, and gender. Category 2 is examination features, which are measured by the physician, such as systolic blood pressure, diastolic blood pressure, cholesterol, and glucose. The third category are the subjective features, such as smoking, alcohol intake, and physical activity, which are given by the patients themselves. The target variable in this classification task is the presence or absence of cardiovascular disease. The big data pipeline chosen for the cardiovascular project comprises Kafka for streaming, Spark for streaming and machine learning, Cassandra for storage, and MLflow for logging and tracking models. Kafka is a high-throughput distributed messaging system. Kafka allows us to take data from different streams such as website events, pricing data, financial transactions, user interactions, or in our case, cardiovascular data. Once the data is in Kafka, we can use it in another system of choice such as a database, analytics system, email system, audit system, or a machine learning application. Kafka has a latency of less than 10 milliseconds when transmitting messages that is enabled by a resilient distributed and fault-tolerant architecture. Apache Spark API combines data and artificial intelligence. It allows large-scale data transformations and analysis and application of state-of-the-art machine learning algorithms. A Spark cluster consists of a driver node and worker nodes. The most basic construct in a Spark cluster is a resilient distributed dataset, otherwise known as the RDD, that is split across multiple worker nodes. The driver node then sends the required transformations to the different worker nodes that carry out the transformations on the chunks of data that they have. Once the data has been processed by Spark, it can be pushed to different output sinks, such as a console sink, which, as the name implies, displays the results on a console, a Kafka sink, which publishes the data to a Kafka topic, a file sink, which saves the data to a CSV, Parquet, or JSON file, or a for each sink, which can save the data to a relational database such as Postgres, MySQL, or a NoSQL database like Cassandra. Cassandra is a highly scalable NoSQL column-oriented distributed database. It can serve as an output sink for Apache Spark or Apache Kafka. At its core, Cassandra can be divided into three different elements. The first element is the key space, which corresponds to the database. Key spaces are also used to group column families or SQL tables, which are essentially an ordered collection of rows and columns. Multiple key spaces are organized by a cluster, which acts as a container. MLflow is a platform for managing the end-to-end machine learning lifecycle. MLflow tracks machine learning experiments from different APIs, including Spark, and compares parameters and results. Moreover, it can also package code in a reusable form for sharing and also store models, making it a versatile tool for building pipelines. To get our pipeline up and running, we first start Zookeeper, which will track the status of Kafka cluster nodes, topics, and partitions. We then launch Kafka. Once Kafka is running, we are now ready to start sending and consuming messages using a Kafka producer and consumer. We also create a key space in Cassandra with matching columns as those in the source or Kafka stream. Following our Spark experiments, we initialize MLflow. The CSV formatted cardiovascular dataset is serialized as JSON events and sent to Kafka. The data is consumed from Kafka by Spark, which writes it to Cassandra for storage. Another Spark instance reads in the data from Cassandra and performs the classification task. For machine learning, I use Spark to ingest data from the corresponding Cassandra table. The data is split into training and test sets. Different transformations such as scaling and one-hot encoding are then performed on the data, after which the data is assembled into a suitable format for machine learning. Once the data is in the right format, we can instantiate a classifier of choice such as gradient boosted trees. A parameter grid can be set up to choose the best hyperparameters using threefold cross-validation. Metrics such as accuracy, recall, precision, and ROC for the best model can be tracked by MLflow. The best model is also saved for deployment. For the classification task, 3 different predictive models were evaluated. The best model was gradient boosted trees with an accuracy score 74%, then random forest with 73%, and finally logistic regression with 66%. All 3 models were simultaneously tracked and saved by MLflow.